Hello, everyone. In this video, we're going to be going over a kinematic problem with two separate objects. This is normally the more difficult kind of kinematics problem in physics, so it might be a little confusing, but stick along and hopefully it won't be too bad. So in this problem, we have a person who starts running with a constant velocity, and he is trying to catch a streetcar, which is 20 meters away. The streetcar is accelerating at a constant 0.9 meters per second squared. In the end, we know that the person runs just fast enough to eventually catch the streetcar and jump on. So they want to know how long did the person run to catch the streetcar, what is the speed of the person when they caught the streetcar, and how far the person ran in total. So the first step you should always have for a kinematics problem is draw a visual. So that's what we've done here. We have one person, which is 20 meters away from a streetcar, and it has a velocity, which is unknown, but it's constant. We'll label that as VP. And the streetcar has a constant acceleration at 0.9 meters per second squared. And we also know the velocity and the acceleration are both in the same direction. So once we have a visual, we can now write down all the variables that we do know. So for the acceleration, you know the person has a constant velocity, so their acceleration will be 0. For the streetcar, the problem told us that the streetcar's acceleration is 0.9 meters per second squared. The velocity of the person, it is unknown, but we know it's constant. So the final initial velocity and the velocity throughout should all just be VP. For the streetcar, the problem stated that the streetcar starts from rest. So we know that the initial velocity is 0. Okay, what else? So we know that the person starts 20 meters behind the streetcar. So what we can do in this scenario is just make the person 0 and the starting place of the streetcar 20. So this will be our 0, that'll be 20, and so forth to the right. And lastly, we know that the person in the streetcar traveled for the same amount of time. Their initial time is the same and their final time is the same. So the unit for time should be the same in both objects. So now we can try figuring out the displacement, the final displacement. So we know that the final displacement for the person is just going to be velocity times time plus the initial position. We know this because there's no acceleration. So the simplest equation we can use is velocity times time. We also know that the initial position we stated was 0. So that will cancel out and we just get the final displacement for the person is the velocity of the person times time. The streetcar is a little bit more complicated. Know that the final position of the streetcar has to take into account acceleration. So we can use the final displacement equals half at squared plus velocity initial times time plus the initial displacement. We know that the acceleration is 0.9. We know that the velocity is 0. And we know that the initial position is 20 based off our diagram. So we can write that 0.9 over 2 times t squared plus 20, because we know the velocity initial is 0, so that'll cancel out. So we're left with this equation right here. Now, before we do anything else, we can also try to figure out what the final velocity for the streetcar is going to be. We know that the equation for the change in velocity is acceleration times time, and since the initial velocity is 0, the velocity final will just equal acceleration times time. And we know acceleration is 0.9, so velocity final will equal 0.9 times the time. So now if we look at these two equations right here, we see that the final displacement is going to be the same. And that makes sense conceptually. If the person in the streetcar catch up to one another, then the final position of where they're at has to be the same. So we can set these two equations equal to one another. So we get that the velocity of the person times time equals 0.45, which is 0.9 divided by 2, t squared plus 20. So this is the combined equation for both of the variables, for both of the objects, and we have two variables in one equation. So we can see that it is much simpler from here. We initially had what, 7 variables. Now we have simplified it to 2. However, we still need to simplify it to 1 variable because we cannot solve an equation which has 2 variables. So now I can look back to the problem. We know that the person runs just fast enough to reach the streetcar. So if the person is running just fast enough to catch the streetcar, that means that at the last second, the person is running at the same velocity as the streetcar. So we know the final velocity of the streetcar is 0.9 t. So we can write the equation that velocity of the person equals velocity final of the streetcar, and then set this equation equal to velocity of the person. So in the end, we get the velocity of the person equals 0.9 times the time. Now, we can look back to this equation and see that if we substitute the velocity of the person for 0.9 t, we're left with 1 variable. And when we're left with 1 variable, we can solve the equation. So if we plug in this variable into the equation, we get 0.9 t multiplied by time equals 0.45 t squared plus 20. And that's just from the equation right here. So now if we try to solve for t, we can multiply the t inside, which is 0.9 t squared, bring the 0.45 t squared to the left, and keep the 20 on the right. That leaves us with 0.45 t squared equals 20, and then t equals 6.67 seconds. And that answers our first question. How long did the person run? Our next question is, what is the speed of the person when they just caught up to the streetcar? Okay, so in our scenario, we know that the person runs at the same speed the whole time. So we just need to find the speed at which the person's running. And in our equation, we can see that the speed at which the person, or the velocity at which the person is traveling at, we designated that as VP. So we know time, and we're trying to find VP. So we can use this equation right here. VP equals 0.9 t. So we can plug that in. So VP equals 0.9, and we said t equals 6.67. So velocity of the person is 6 meters per second. So that will answer number 2. The last question is, how far did the person run? Okay, so far we know time, know the velocity for the person. So to figure out how far he ran, we can just use this equation right here. Our velocity times time equals the final position. So final position equals 6 times 6.67, because that's the velocity and that's the time, that equals 40 meters. And to find how long he ran in total, we can subtract the initial displacement from velocity, which is 0. So we're left with 40 meters. And so for the last question, how far did the person run? We know that the person ran for 40 meters. So that solves all 3 of the parts of the problem, and we are done with this question. So I hope that was helpful for you guys, and I will see you guys next time.